Okay.
So hello everyone for another session of Symmetry seminar. Today we have Miguel Montero from IFT Madrid, and he will tell us about the Chronicles of IIBordia. So please go ahead, Miguel.
All right. Thanks a lot, Laksha, and the other organizers for putting together the nice seminar series and for the interest in our work about our adventures in the lands of IIBordia. So first things first. This is, it's always important, and all the more so in a Zoom seminar. Please interrupt me, okay, at any point. I know you guys will do it anyway, but I just wanted to give a heads up, particularly to the younger people as well. Just interrupt me at any point with questions, any comments you might have, whatever it is. Please just stop me at any point and just go ahead. So I thought that this being a Symmetry seminar and the main lesson of this talk being very directly related to symmetries, I thought I would just give it on the first slide. So I'm going to first give you the main lesson, the take-home message. If there's one thing that I want you guys to take home from this talk is this, and then I will tell you everything that we did. So the basic lesson is that we can actually, we are used to learning a lot about the theory from the fact that it has symmetries. But interestingly, we have discovered in the recent years that we can learn a lot, not just from the presence of symmetries, but also from their absence. Sometimes you have something that looks like a symmetry, but which is actually broken. And the way it breaks can tell you something very, very interesting about the underlying physical theory. And this talk is just about that. So more concretely, we will see how applying this principle of learning about the theory from how the symmetries are broken, we will apply this idea to type 2B string theory to recover a bunch of the knowledge that we already have of type 2B and get a few new things. More outstandingly, a new non-supersymmetric brain in type 2B string theory. And the main tool that we will be using is it's a set of ideas which go under the name of covariatism conjecture of McNamara and Baffa, they published in 2019. So I will be explaining that as well. In fact, the plan of the talk is this idea of using breaking of symmetries in quantum gravity to learn about the theory itself is part of a bigger picture, which is called the Swamplan program. So I'm going to give you like a one-slide introduction to what the Swamplan is and what is the reason why we believe that absence of symmetries can be useful, which is the idea there's no global symmetries in quantum gravity. Then that's going to be a very abstract discussion. We'll make it more particular for this covariatism conjecture, which will be the tool we will actually use to constrain effectively theories of interest. And then we'll apply it to 2B. And then we will use these techniques to get new objects and predict new defects in type 2B string theory. And finally, we'll get to conclusions. Okay, so that's the big picture. I don't think there's, well, are there any questions so far? Yeah, okay, thought as much. And let me just emphasize that this is based on a big paper that we put together with Marcus Dieriegel, Jonathan Heckman, and Arun De Brave. And to compute the covariatism proofs of type 2B, there is a whole math story, but that belongs to another talk. This is a physics talk. So we're very proud in our paper in the third page, because since we call it like the Chronicles of IIBordia, as if it was kind of like the Chronicles of Narnia, we felt it had to have like a map, like the maps that you can find in Lord of the Rings or Chronicles of Narnia, that kind of stuff. So we wrote a map of the paper, like the different paths you can take. You can take the path of the busy professor, which takes you directly to the pond of conclusions if you're busy. And today we're going to take the path of the physicist, but there's a whole other story with all the mathematical details, complicated details that we need to compute these covariatism groups, which would not have been possible. I really want to give a shout out here to Arun, our mathematician. He's absolutely amazing, and he's always interested in working in covariatism in physics. So yeah, it's just a great guy if you want to contact him at some point. So Swamplan, what is the big context of the idea there's no global symmetries in quantum gravity? So this is the idea of the Swamplan. The idea of the Swamplan is that unlike it might seem at first sight, you might think that you can couple any quantum field theory to gravity. It's very easy. Just pick the Lagrangian, just write down this thing, write your Lagrangian, change all derivatives by covariant derivatives, and couple to the metric like this. And then this is how you couple any Lagrangian you like to gravity. And this is certainly okay perturbatively and to any order in G Newton, but we have there's a growing body of evidence that this is actually not okay at the non-perturbative level. Not any low-energy effective field theory can be consistently coupled to quantum gravity. So you end up having a picture like this big blue blob, which is the space of all quantum field theories. Most of them are not okay with quantum gravity, and there's a small subset of them which are, and this is what is called the landscape. And those effective field theories which are not, they cannot be consistently coupled to quantum gravity in a straightforward way, are said to lie in the swampland. And people who work on the swampland, we try to determine the non-trivial properties that quantum field theories in the landscape must satisfy. And more generally, we often go, and in fact, in this talk, for most of the talk, I will go beyond the low-energy effective field theory to try and constrain, to see what quantum gravity can tell you about the spectrum of extended objects that you can have in your theory. Okay? So the way we go about this idea is we try to come up with what we call swampland constraints, statements about quantum gravity that we feel we believe are true. And by far the oldest swampland constraint in the book is that there's no global symmetries in quantum gravity. Okay, we believe that there's no global symmetry in quantum gravity. What that means is that if you have a charge which is exactly conserved, it has to be a gauge charge. It is a charge that you can measure from afar. Now, we have lots of evidence for this. You can make some black hole arguments involving decay of black holes. There are recent proofs using the Euclidean path integral in restricted contexts. This one I particularly like. For continuous global symmetries, it is actually equivalent to Noether's theorem of the dual field theory in 8A CFT. You can prove it in perturbative string theory, and it is true in every string theory example. So what that means is that if you write down an effective field theory and it looks like it has a global symmetry, that is actually not true. It's better, it has to be either broken or gauged by non-perturbative effects. Any questions about this? Okay. So the way I was, discussing before, I didn't say what was the dimension. I was talking about the symmetry. When you talk about the symmetry, you're implicitly talking about charged objects, but I didn't say anything about the dimensionality of those objects. And in fact, most of these arguments apply not just to zero form symmetries, but also to generalized global symmetries for which the charged objects are extended. And in this particular case, the principle in a sense becomes more powerful because you can use it to predict the existence of objects in the theory. So for instance, imagine that you have just Maxwell theory. You have an effective field theory Lagrangian, which is just Maxwell coupled to gravity. Maxwell theory has a Bianchi identity and an equation of motion, which are precisely the conserved currents for two one-form symmetries. The charge operators under these one-form symmetries are Wilson lines and Toff lines. Okay, you can think of them as the Ward lines of very massive electrically charged particle or monopole in the theory. And since we believe there's no global symmetries in quantum gravity, the actual conservation laws cannot be exact. They have to be broken. And for them to be broken, the simplest way to do it is to change the right-hand side and make it non-vanishing. In the case of Maxwell's equation, what you do is you add electric charge here. And what that means now is that the Wilson line can open by you adding a pair of electrically charged operators. And similarly, for magnetic symmetry, you can now open up the Toff line and by nucleating a monopole-antimonopole pair. The fact that you can do this, that you can open up the Wilson lines and the Toff lines like this, means that the corresponding symmetries are not exact. The symmetry is not conserved. And well, since we can do this, if you think about it, what happened here is that this idea that you started with Maxwell theory, there were no charged particles. And just from demanding that there's no global symmetries, you're forced to conclude there's electrically charged objects in the theory or monopoles. Okay, so just this principle that there's no global symmetries in quantum gravity tells you that there's a charged object, something like an electron on a pole or a monopole in this theory. So it's telling you something non-trivial about the non-perturbative spectrum. So that is the basic mechanism that we'll be using later to construct branes in type 2B string theory. We're just gonna, this talk is about constructing a bunch of currents or constructing a bunch of symmetries and charges for type 2B string theory and finding the branes that you need to include to break those symmetries, okay? And the only thing that is special about these symmetries is that they are not that obvious from the effective field theory. They have to do with this covariance stuff. But the basic idea is already on this slide. Any questions about it?
I have a question.
Yes, please.
I mean, in the standard model,
Yes.
we do have a theory which looks a lot like this.
Yes.
So what's the get out in that case? There is a U1. Have you proven that there is a monopole?
Right. No, we haven't proven there's a monopole, but yes, what this is telling you is that there has to be a monopole in the standard model, right? Now, you should notice that I haven't told you anything about the properties of this monopole. I haven't told you its mass. It could be like a black hole with magnetic charge for all I care in this argument. So it's not really a very strong constraint at low energies, but you have learned that such an object exists in theory, if there was any doubt.
Thanks.
Good. Very good. Any more questions? Good. Excellent. So, as I said, absence of higher front symmetries predicts new charge operators or states. So the idea here is we just get an interesting effective field theory coupled to gravity, whatever you like, and use it to learn about the spectrum of charge extended objects. So we're just discussing about the standard model and monopoles, but for instance, if you do it for type 2A supergravity in 10 dimensions, it has a U1 field, and then you predict the existence of D0 branes. And so the more, the way this goes, right, the more effective field theory symmetries we can find, the better. And this is why I'm gonna tell you a particularly useful way of obtaining some kind of a bit weird looking symmetries that we don't usually talk about, but which we believe are present in any effective theory coupled to gravity, which are very interesting. They're these covariance symmetries. Okay, so I am now going to construct a new kind of charge object involving the topology of spacetime, and that charge is going to lead to a global symmetry. Indeed, the basic idea of the covariance conjecture, of this covariance idea, is that if you have spacetime with non-trivial topology, this can lead to global charges. So how does this go about? Well, just to keep it very concrete, just to explain it by an example, let's imagine that we take 5-dimensional theory of gravity. It's your favorite 5-dimensional theory of gravity. Maybe it's M theory in your favorite Calabi-Yau, or maybe it's just pure 5D gravity, if you believe such a thing exists. And then we look at it at the t=0 slice. So we just look at the constant time slice, which looks like R4, okay? And on this R4, you just have empty space. You can do whatever you like there. I'm gonna do something funky. I'm gonna take a K3, which is, for those of you that might not know, it's a compact manifold that we like a lot, has interesting topology. It has non-trivial topology, and I'm gonna glue it to R4 like this. What does this tube that I'm drawing here means? What that means is what it's called the mathematician's connected sum. I'm gonna take a little 3 sphere out of the R4. I'm gonna take a little 3 sphere out of the K3, and I'm gonna glue them, okay? So I do that. And what is the configuration I am left with? Well, away from this hole, it kind of still looks like R4. You didn't do anything funky. So this looks like a localized particle in R4. And in fact, that's what it basically is. We constructed something like a K3 particle using topology of spacetime. And in fact, this particle carries a lot of conserved charges, because if you imagine changing the metric by a little bit, topological properties of the K3, such as its metric, such as its intersection form, will not change. So it looks like we have constructed a new particle in this 5-dimensional theory of gravity. And indeed, it looks like could do this thing with any, other 4 manifold you would like of non-trivial topology and get many, many different particles, okay? So it looks like I can construct like a plethora of different particles by gluing topology like this. However, there is one subtlety that we need to take into account, which is that, well, if I am constructing this particle because, I think topology maybe is dynamical in quantum gravity, so I can do something like glue this K3 particle or something like that, then it better be the case that I make sure that the K3 itself cannot disappear by some topology changing process. We know that topology changes in quantum gravity. We see it every day in 80 CFT. And the worksheet, every time that you compute anything non-perturbative, you have a summary topologist. So it could be that if this is my K3, there's something like a Euclidean instanton that changes its topology. And so here I'm drawing something like a Euclidean process where one manifold, okay, this is Euclidean time, maybe as you progress in Euclidean time, it grows, holds, and reattaches. And by the time you're done, you get a very different topology, okay? So this kind of topology changing transitions, you would expect they exist in any theory of gravity. And so the only kind of topology that could potentially be invariant under these deformations is anything that is invariant under this process, okay? So this process that I drew here, where you have one manifold that's the initial state and another manifold is the final state, and the two of them together are the boundary of another manifold C of 1 dimension more. This is what it's called a cobordism, okay, between M1 and M2, between these two manifolds. And so this set of cobordism classes, it turns out that it has a group law. It satisfies a group law. It's called the cobordism group, and it is precisely this cobordism group, the set of charges that you can construct with topology in any theory of gravity, once you take into account equivalence and then topology fluctuations. So for instance, the K3 I gave you before, okay? This K3, it turns out that is in a non-trivial class of this cobordism group. So what that means is that there is no way that you can get rid of it by these topology changing transitions. It is actually some sort of conserved global charge. Okay?
Question?
Yes, please.
So why do you only allow cobordisms? I could envision some other kind of transformation. So for example, we know that there are transformations, topology changing transformations involving Landau-Ginzburg models.
Very good. This is exactly where I'm going, Laksha. So the point of view that we have here, okay, is that we want to apply this to any effective theory that we want, or to an effective theory in which we actually don't know which singular configurations are allowed. So for instance, indeed, in string theory, you could do Landau-Ginzburg, you could go through conifolds, you could go to all sorts of non-smooth configurations. In a general theory, I don't know if those are allowed. So what the cobordism captures are the symmetries that are good symmetries of the effective field theory. In this language, I would say that the Landau, this is what I'm getting to actually. I would say that the Landau-Ginzburg configuration allows you to kill some of these global symmetries, because it's a configuration which is singular. You're going to see from the point of view of effective field theory. Did I answer your question?
Yeah, I'm still a little bit confused because I'm thinking now that you will argue that there must be dynamical objects for the cobordism group that is remained. But if you include Landau-Ginzburg models, that might reduce the group that you have for which you need to include.
Okay, so so this is exactly where we're going. So if there's any other questions about this part, I can answer them now. If not, I'm going to go to address your question right now.
Yeah, thank you.
Any more questions about just the basic idea of what the cobordism is and this topology and transitions? Okay, then let's go with Laksha's question. So just as a caveat, just as a simple remark, when the manifold is itself a boundary, that means that the symmetry is broken because it's charged. Here there's nothing. There's the vacuum. So when a manifold is a boundary, that means in the trivial covariance charge, there's no symmetry. And as I was saying, the covariance groups, they capture these topological charges that cannot be killed via smooth topological transitions, okay? They capture the stuff that cannot be killed once I take into account that they can do interpolating smooth manifolds. In other words, the things that you can describe with the low energy effective field theory. But I was telling you before that there are no global symmetries in quantum gravity. So it must be possible to kill this, to show that even these charges that are non-trivial in the covariance, there has to be some possibly singular object from the point of view of the effective field theory that kills those charges. And so, and I think this is what you're going to, Laksha, once I take into account all of these defects, because I believe there's no global symmetry in quantum gravity, it better be that once I take into account all the defects, there's nothing left. And this is the intuition you were explaining, that once you take into account things like Landau-Ginzburg models, the group gets smaller. Now, if I was just talking about Landau-Ginzburg models, I wouldn't need all this whole discussion. I would just talk about Landau-Ginzburg models. But the point is that this principle is general. There are sometimes some cooperation classes that are perhaps, they involve things that cannot be described in the worksheet. And then the power of this approach is that it tells you that even in those cases, there has to be such a defect. And you can actually learn things about the defect, as we will see. And this is the whole point. Killing these new global symmetries forces the interaction of defects. Is it clearer now, Laksha?
Yes, thank you.
Thank you. Very good. So killing this global symmetry forces the introduction of defects. And just to make it a bit more precise, if you have a quantum gravity in d dimensions, the covariance group of p-dimensional manifolds, omega p, describes charged objects of dimension d minus p minus 1. So for instance, before we have 4 manifolds, so it was p equals 4 and d equals 5. So this is actually a 0-form generalized global symmetry. And absence of global symmetries means that we must introduce singular objects that kill all these classes. Okay? So this is the general idea. Let me just illustrate that with a couple examples. One example is the K3 I was describing before, but let's just be concrete. Let's just try to ask what happens if you put a K3 in type 2A string theory in the manner that I was putting before. Is it a boundary? Well, cannot be the boundary of a smooth manifold, as I was saying, because it's in a non-trivial class of this covariance group. But actually, type 2A is just M theory on a circle. So if I uplift to M theory, this K3, this configuration is actually M theory on K3 times a circle. And in fact, it turns out that the 5-dimensional Bordian group vanishes. Okay? So what that means is that there is some configuration, some M theory, the K3 times a circle is the boundary of some configuration in which the M theory circle is doing funky stuff. It's degenerated, it's becoming very small. So this is an example. It's something which is going to be non-perturbative from type 2A perspective. But in this case, it is simple enough that you can study it in M theory. So, it's interesting. But if this is all there was, you wouldn't need to cover this. You would just discuss this example.
I have one more question.
Please.
So you're using in these Bordian groups the spin structure.
Very good.
There could be these higher form gauge fields which might impose some extra structures that you need to include.
Yes. Laksha, it's the second time now that you're describing what is coming in the next slide. So that's great.
Okay, sorry. I'll do it again.
No, it's amazing. It's amazing. The answer is that indeed I'm putting spin structure here simply because type 2A has fermions. Mm-hmm. In general, of course, there could be other backgrounds, which in this particular, for instance, you could turn on Ramon fields on the K3. I'm choosing to turn them off for this particular background, for this particular question. But of course, the most general question involves turning all of those on. And the more backgrounds you turn on, the more complicated the question is. And in fact, for instance, the actual calculation that we did in this paper, we were just turning on these backgrounds for the duality bundles in type 2B string theory. So for instance, we were also turning on Ramon fields to 0. Okay, we're just asking a simpler question.
So if I turn on more backgrounds, do these groups become smaller and smaller?
Sorry, if there are.
If I turn on more and more backgrounds, do these groups become smaller and smaller?
In general, they become bigger and bigger, right? For instance, imagine a 5-sphere. Five-sphere is trivial in boardism. It's just the boundary of a ball. But 5-sphere with any initial Ramon flags is not. You need to put D3 brains to yeah. So in general, they get bigger. Both, we will see examples where both can happen, because sometimes enlarging the boardism group allows for more cobordisms, and so the overall thing is smaller. So it can go both ways. That's the long story short.
Okay, thank you.
Any more questions?
So I'm not quite sure I understand how this solved the particular problem. I mean, you uplifted from type 2A to M theory, and you said, oh, K3 cross S1 is trivial in spin boardism,
Yes.
but K3 still is not, right? So now we're in a new theory, M theory, rather than type 2A, and we still have a group, cobordism group to get rid of.
Yes.
We haven't gotten rid of omega 4 spins. We've just moved it to a different place.
Yes, that is excellent question indeed. So there's two points here. So the particular class of type 2A on K3, it's indeed K3 times circle, but you're completely right to say, well, fine, but then I'm just gonna ask about omega 4 in M theory already, okay? Now the answer to that one is a bit more complicated. So first of all, M theory has a parity symmetry. So what you need to look at is not omega 4 spin, it's omega pin plus spin. And there's a cobordism in omega pin plus between K3 and I think 8 copies of RP4, okay? And for the RP4, you're out of luck. You're not gonna be able to find a boundary for it in effective field theory, but RP4 is precisely the boundary of the OM5 plane. So if you keep pulling down the thread you were just asking, you would have been led to discover the OM5 plane if it had not been discovered 25 years ago or 30. Did they answer your question?
Yeah, great, thank you.
Okay. And there's another question, I think. Someone raised their hand? I think
Can you unmute yourself, David Costa? Maybe it's just a stray hand.
Okay.
Sorry.
Yes. Hello.
It was a mistake. Sorry.
Okay. Well, no worries. Well, yeah, just another simple example, just to connect what we're saying before. If you have a U1 gauge field, you could consider a sphere with flux, and then the thing that is going to kill that sphere with flux is the monopole we're talking about before. So you're recovering all the stuff that you could say before for ordinary symmetries, okay? So it's a neat way of talking about symmetries in effective field theory coupled to gravity. And indeed, as Laksha was pointing out, and I think these examples illustrate that very often is the case that you want to endow your manifolds with some additional structure. If you have fermions, surely you want a spin structure. If you have fermions with parity symmetry, as in M theory, you want some kind of pin structure. If you have Ramon fields, you can also add them, or fluxes, or whatever. And the basic idea is always the same. Just take the picture I gave you, and whatever structure you have here, spin structure or gauge bundle, whatever, you demand that it extends smoothly on C. And of course, that alters the cobordism group, and it alters its computation. It makes it more complicated. How do you compute cobordism groups? Well, essentially, the cobordism is actually a generalized cohomology theory, so you can use techniques from the Adam spectral sequence and the Atiyah-Hirzebruch spectral sequence. We use both in the calculations of the cobordism groups that I'm going to be telling you about. But essentially, that's the basic idea, the basic framework that we want to use, this cobordism conjecture. So now that we are armed with the powerful sword of cobordism, we are ready to venture into the lands of IIBordia. So what are we going to do, really? So we're going to compute the cobordism groups of type 2b supergravity. Of course, we're interested in this because it's the low energy limit of type 2b string theory. And the one thing that we're going to do, which is it's not just, it's on top of just the vanilla geometric spin Bordesian groups is that we're going to introduce a duality bundle. What do we mean by that? Type 2B has a duality symmetry, and for instance, we're going to allow for circles where as you go around the circle, you pick up an action of the duality symmetry. Okay. This is still smooth configurations of type 2B supergravities. No 7 branes, no nothing. For instance, something like a circle with a duality with an SL2Z action is okay. And we're going to compute these groups, and then we're going to find that there's a lot of them which are non-zero, and then we're studying the defects that are predicted by the covariance conjecture in this setup. And we will recover actually a lot of supersymmetric branes, and we will also find a few new ones along the way. Okay. So
yes, I was going to ask this question, and I'm sure you're going to answer it in a subsequent slide. But there's a question about what you count as a global symmetry, in particular, if it's spontaneously broken. Does it count? Because that's precisely the sort of setup in the case of this duality symmetry.
That is absolutely right. It still counts. I think it still counts. So, for instance, like some of the arguments that I was, like in the first slide I was telling you, that has to do with black holes evaporating and stuff. Some of those arguments are sensitive to the symmetry being spontaneously broken, but others are not. For instance, if you imagine a continuous spontaneously broken U1 symmetry, it is still true there's a conserved charge in dual CFT, right? And then you can still couple to a background gauge field for that, and therefore it becomes a dynamical gauge field in the bulk. So yes, and in fact, in the particular case of type 2B, I am on even better ground because I for sure know I can turn on bundles for these guys. Yeah. Okay, I'm just gonna say I'm just gonna go crazy looking at configurations of type 2B with duality bundles and demand that all of them can be deformed to the trivial class. That's what I'm gonna do. Sounds good?
Yeah, I mean, in some cases, there are fixed points of the duality group, and so you could imagine.
We will see those.
Right. Yeah, exactly. But I mean, in general, I might have missed stuff, right? That there'd be no fixed, that there'd be elements of the duality group that there have no fixed points, and so there's no expectation values for the scalar fields in type 2E that are invariant under that subgroup.
Yes, that is true. The computation of the covariance is interesting, actually. The computation of the covariation group, which gives you a bunch of generators, which I'm just going to show you now. Oh, well, first I need to tell you something else, but I'm going to show you the covariation groups in a couple slides. And each of those guys, we could identify a generator, and all the generators have an unbroken subgroup, which is precisely right to be compatible with the order of that factor of the group. I'll come back to this.
Okay, right.
Good. So before I get to Jack's question on the covariation groups, I need to tell you a little bit more about what is the duality symmetry of type 2B string theory. Now, this is a question you might think it's obvious, it's like SL2Z, but it's actually a bit more complicated. So just to get back a little bit, since I said I was starting with type 2B supergravity, type 2B supergravity has on the nose an SL2R symmetry, global symmetry, which it's broken in type 2B string theory by quantum effects, by D-branes, however you want to say it. And it actually has a geometric interpretation in F theory. This SL2Z is just the mapping class group of the F theory torus. And in M2F duality, this is related to diffeomorphisms of the dual, now physical M theory torus. Great. But if you buy this picture, then you start seeing that there's a bit of nuance here, because M theory and type 2B and type 2B string theory, they have fermions. Okay, and this mapping class group has transformations like rotating the torus by 190 degrees or 90 degrees, things that on bosons, like rotation by 190 degrees for bosons squares to 1, but for fermions squares to -1. And so that means that if you include the action on fermions, the actual duality group of type 2B gets enlarged by fermion number to something called the metaplectic group. But even this is not the end of the story, because as we were discussing before, M theory has reflection symmetries. And because you have reflection symmetries, you can flip one of the sides of the torus. That actually enlarges the group from SL2C to GL2C. And if you take into account that you can have reflections and fermions and everything, you end up in a bit more complicated abstract group, which is the pin plus cover of GL2C, some group, okay? The point here is just that it's just not the SL2C, it's a bit more complicated. And this is the actual duality group of type 2B string theory. So you could say there's 3 approximations to the duality coverdistant groups. One of them that just takes into account, forgets about the spin structure and stuff, which we actually computed, but just as a warm-up, so to say. It's not very interesting. You can take into account the fermions, forgetting about reflections. This is actually a physically interesting thing to do. You're just saying that you're not going to consider identifolds. And finally, you can take everything into account. And this gives to 3 different classes of coverdistant groups, which we denoted like this. This is coverdistant groups with a spin MP structure, because the fermion number of the spin part is mixed with the MP part. And this is the same for spin GL plus structure. So there's 3 different structures that we can look at. And in our paper, we computed the coverdistant groups of type 2B string theory in all these approximations. And this is how the thing looks like. There's a bunch of coverdistant groups. Each of these is potentially, it's potentially a global symmetry, okay? That we need to introduce a defect to kill. So it's a potential to learn a lot about type 2B string theory. So for instance, I will be going down the examples, down the classes, giving you examples of generators, and you will see, Jax, that for instance, here, we're gonna go to here, this right now, omega 1, it's just circles with bundles. The coverdistant classes here admit representatives that have some subgroup of MP2C unbroken. For instance, this C3 has to do with the U generator of SL2C, okay? So this always happens in all these classes. Are there any questions so far?
Could I ask, what is the physical reason that you want reflections to square to 1 and not -1 to the F in the pin plus cover?
Excellent. I should have said that. I actually should have said that before. It's because the connection to M theory. Okay, M theory, because by going the duality to type 2B to M theory, you relate the reflections of the duality symmetry here. They become physical diffeomorphisms in M theory, and in M theory, parity squares to +1. Why is that? Because M theory has supersymmetry in 11 dimensions, and the only the supercharge is in the Majorana representation, and it only admits a pin plus symmetry. It doesn't admit a pin minus.
Okay, thanks.
Yeah, this is explained. I cited this paper by Tachikawa and Yonekura about fractional types of identifolds. This is a great paper. They explain this in the appendix.
Great.
Okay. So yeah, we computed this, and then we found all the classes. And now I'm going to tell you something about the generators and the defects that we get. So we've spent 40 minutes building up. Let's reap some rewards. Okay, let's start with omega 1. Omega 1, it's the space of one-dimensional manifolds with a spin MP2Z bundle. Sounds complicated until you think that, you know, as far as one-dimensional manifolds go, you essentially just have the circle, and the only bundle that you can put on a circle, you just specify by a group element, which is the holonomy you pick as you go around the circle. So actually, all these classes are very simple. And in fact, this C3 is just a circle with an holonomy of the U generator of SL2C, and the C8 has to do with the S generator, which becomes of order 8 once you include fermions. So the coverdistant conjecture tells me that these guys must be boundaries of some other guy. And by the time I write a picture like this and say these words, it's pretty clear that I'm talking about 7 branes. This is the standard picture for PQ7 branes. You just have a circle with an SL2C monodromy, and the SL2C monodromy gets you what the 7 brane is. So the coverdistant conjecture is predicting PQ7 branes. Okay, we recover that. Actually, it's interesting because once we have the 2 7 branes that are associated to the generators of these 2 guys, we can recover any other 7 brane by moving them around with monodromy. So actually we recover all 7 branes. So that's a nice start. You get back the good old 7 branes. So let's move on to something perhaps a bit more interesting. Omega 2 vanishes, so let me go to omega 3. This is Z2 times Z3 plus Z3. And we were actually able to find out that these are generated by lens spaces, okay? So now what you do is you have something like a 3-sphere with a quotient. And for instance, on this example, on the S stream of Z4, you actually need to turn on a duality bundle around the non-trivial 1 cycle of this space to generate the vorticen class. This spaces, okay, the lens spaces, you can actually see as vibration or circle vibrations over S2, and to since MP2C is the spin cover of the diffeomorphism group of the torus, if I give you any duality bundle like this, you can give me an associated torus bundle where the torus actually is not pinching. Okay, it's just a torus that has the transitions functions specified by my duality bundle. So if you do something like that, so this would be like the F-theory torus. The configuration that we are constructing here is a non-trivial vibration, but the fiber never pinches off. You see where we are going. If the fiber never pinches off, well, we just need to find a configuration which includes this, where the fiber does pinch off. And this lens space is actually the boundary of this space, of the O minus n bundle over P1. And this space itself is one presentation of what are called in the F-theory literature non-Higgsable clusters. These are particular singularities that are particularly nice because they are what appears in F-theory configurations once you've Higgs as much as you can. So they're important objects, for instance, the construction of 6D CFTs. So omega 3 predicts the non-Higgsable clusters. That's great.
Can I ask a question, Miguel?
Yes, please.
So you only have very specific n.
Yes,
for
yes,
the
good,
NHCs,
good.
you have other values as well.
Yeah. Indeed, that's a
what
good question.
happened
I
to
don't
those?
know the answer to actually. We just get a couple. Indeed. Yes. So we just get. You should have written it here. I should have written here. Some.
Do you get all which don't have a singular boundary?
Say that again. Sorry.
Do you get all which don't have Kodaira singularities hitting the boundary, or is it even a subset of? I think it's like n 3, 4, 5, 6, 8.
It's a subset because just 3 and 4.
For instance, the 5, exactly. The 5 we don't get, for instance, the 6. The 6, I think, is coordinate to the other 2, but in fact, they should be coordinate to each other because that's what we computed, sort of. The boundaries, the smooth asymptotic boundaries, for instance, the one with Z6 is coordinate to this guy. So at least as far as conserved charges are concerned, we're indeed saying that the non-Higgsable cluster with the Z6 is coordinate to this other 2. That doesn't mean they're the same object. It means they have the same coordinate charge. Okay.
Okay, thanks.
Any more questions? Good. Let's keep going then. It's a bunch of coordinate groups. So omega 5 again generated by lens spaces, and this time what we rediscover are the S-folds. Okay. So you see, by doing this technique, we are rediscovering things that were discovered later and later. So we started with the 7 branes, then we went to non-Higgsable clusters, and now we're in S-folds. And actually, we have already found out something that there's actually, this one is not really new, it's discussing some old paper. But for instance, we find an n=1 cousin of this S-fold. So this S-fold, the S-folds, they have n=3 supersymmetry in 4 dimensions. But if you tweak the spin structure a little bit, you can find an n=1 cousin. And M-theory counterpart of this guy was described in this paper. So this is something we're thinking about right now, try to understand, for instance, the central charges of this guy, whether A is equal to Z exactly, or, there's a bunch of interest. There's another CFT that you can get like this, which just has n=1. Very good. So what else is there? Well, omega 7 and omega 9 are also generated by lens spaces. Okay, so it's a similar pattern. And actually, it is interesting. This is something that we haven't quite figured out. We want to think about a bit more. But if you do a naive computation of the supersymmetries, for the same reasons that when you compute the supercharges that are preserved by an S-fold, in fact, you get funny stuff like n equals 3. Here we seem to be getting 8,2 supersymmetry, although we're not quite sure because one needs to take into account Ramon fluxes and other stuff that we didn't take into account. But I think there's a possibility we get something which has 8,2 supersymmetry, what we call S strings and S instantons. And finally, there's just one class which just comes from wrapping an S-fold with a topological twist. Okay, so sometimes you are not discovering new objects. Sometimes it's just interesting compactifications of the objects you had before. Okay, so I've discussed all the omega odds together because they're all length spaces, so they can be discussed uniformly. Before I move on, are there any questions about any of these guys? Very good. So let's move on then. So what about the even dimensional groups in spin and P? All the even dimensional groups vanish except for omega 4. We were discussing before that omega 4 spin is generated by K3, but the spin and P version of it is generated by the Enriquez surface. So what is the Enriquez surface? The Enriquez surface is some quotient of K3, which is not spin, but it is spin and P. And actually, people have discussed the fact that there's a Calabi-Yau manifold, which is a T2 version of the Enriquez surface, is called the Enriquez Calabi-Yau. We are rediscovering the Enriquez Calabi-Yau. So far we have rediscovered a lot of stuff, and maybe these exotic strings which we didn't really study that much. In omega spin and P in 8 dimensions, is generated by a spin manifold plus the quaternionic projective plane, and these two are the same as in spin. So actually the MP didn't bias anything here. And finally, interestingly, for omega 10, we find the Z2, and omega 10 in a 10-dimensional theory is classifying topological couplings that one can write down in 10 dimensions. So for us, the interest in omega 10 is not so much you know, they could be related to covariant classes of Euclidean compactification, whatever that means. But really, the reason why we're interested in omega 10 is a bit different. We're interested in it because it classifies discrete theta angles that you might couple to type 2b supergravity. And since the story for this guy is richer in spin GL, I'm going to discuss it later with spin GL. Very good. Again, you please interrupt at any point if there's questions or I mean, you guys are doing it, it's great, but just one to remind. Anyway, now let's look at the real thing. Let's look at the big covariant groups omega spin GL plus 2Z. And doing this just means that we are now actually including actions of reflections of the F theory torus, which in type 2B language, they correspond to minus left moving worship fermion number and omega, the omega you use for orientifals, okay? Good. So let's do the same thing. Let's first look at the first covariant group, which as you know now, captures 7 branes. So you expect to find the 7 branes, the PQ7 branes, so you would be wrong. Turns out that the first covariant group in a spin GL plus 2C is just 2 C2s. So what is going on? What happened to our 7 branes? We were predicting them and we are not predicting them anymore. Well, kind of. This is related to a point that Lakshya raised before, that sometimes by enlarging the group, you can actually get more covariatisms, and things that were non-trivial before become trivial after. And in fact, what this is telling you, something I didn't know about, which I thought it was quite funny, is that the branes, the PQ7 branes that we do in F theory, actually, to the extent that they are defined by the asymptotic holonomy of the axial dilaton, or the duality bundle, you can actually construct with smooth configurations, okay? You can do the following. It's described in this paper by Jack McNamara. You take a torus. Along the torus, you put holonomies A and B in whichever group you like, and you glue it with the connected sum. Then the holonomy asymptotically is A, B, A minus 1, B minus 1. It's the commutator. And what that means is that you can construct with smooth manifolds any configuration which is a commutator. And it turns out that for instance, the U generator that was giving us a 7' before is a commutator in spin yield plus 2zip. And so you can construct it in smooth ways. So that's what we learned. You can actually geometrize the 7 themselves. But then what are the 2 C2s that we get here? Well, these are classes of circles with it's like the F theory story, only that we glue the torus by a reflection. So that means, on one hand, that means that these guys are necessarily non-supersymmetric, and the defect that you need to put in the center involves a reflection, which we call them reflection 7 brains. So now, finally, the covert descent conjecture has predicted for us a non-supersymmetric 7 brain. So this is something that you could not get in, I think, from other perspectives. So there are 2 reflection 7 brains, one associated to a holonomy of -1 to the FL, one associated to a holonomy of omega. They are S-dual to each other. They allow you to fractionalize an I0 star singularity. And it's a very interesting brain because it gives you a check of the covert descent conjecture. This brain is hopeless. It is strongly coupled at its core. We actually argue that it cannot be described in the string worksheet as an orbifold. Basically, everything that you can write down won't describe it. And so it's a very weird kind of non-perturbative object, but you can actually learn something about it via anomaly inflow. So what we did there, you can write this reflection 7 brain as the boundary of a very long cigar. So you can draw this disk as a cigar. And then you can actually, far away from the R7 brain, you can compute one loop Chern-Simons terms in the action. And these one loop Chern-Simons terms, they actually are related via anomaly inflow to the work volume theory of the R7 brain. If the R7 brain didn't exist, if the covert descent conjecture was that all the configurations have a boundary was not working, these anomaly polynomials would have any coefficients, could have gotten anything like that, because they come out by adding up things in kind of a random way. But when we did the calculation, it turns out that they exactly conspire to give you an anomaly polynomial of 1 Dirac fermion of R charge 1/2, what you would expect for a Goldstino, because this guy is breaking supersymmetry. So it is an indirect check that this object exists. I'm going to tell you now a bit more about the work volume of the R7 brain. Just wanted to stop to see if there's any questions about it, and also to check on time. I might go 5 minutes over time, if that's okay with you, Laksha.
Yes, that's fine. So I also have a question.
Yes.
So suppose I did not know about the existence of PQ7 brains.
Yes, yes.
And I computed this Bordism group, the previous one, and then I would compute the new one and then find that, okay, I don't need to conclude the existence of new brains.
Right.
So I could apply the similar logic also to this R7 brain.
Well, sorry. So for the let me go back to the example of the 7 brain. So this object that we constructed here, okay, it's a smooth configuration, okay. But if then you decide that you don't want to use reflections, you forget about them, it kind of looks like a 7 brain, like a PQ7 brain. So this calculation is not invalidating the previous calculation, okay? It's just telling you that if you have more, more symmetries that you can use, you can construct more stuff, and stuff that looks singular to you can be geometrized. So you could think of this guy as perhaps some absurdly excited state of a 7 brain, but the 7 brains are there. Okay, it's just the fact that they are not detected with this Bordism group means you need to work a bit harder to construct them. But it's the same. And for the reflection 7 brains, it would be the same. If there's a refinement of the story that allows you to, in some stringy way, geometrize the reflection 7 brain, well, that is great. Then you won't see it in the corresponding covert descent group, and you will have a better understanding of it. But the fact that you identify that it has to exist from this picture is still the same.
So I thought the logic was to identify some geometric configuration which cannot be trivialized, and
Yes.
then saying that I have a brain in order to trivialize it, in
Yes.
order to non-geometrically trivialize it.
Yes.
But in the process, I can use any kind of fields that my string theory or M theory has.
Yes. Yes.
So
Well,
that's why I thought I cannot conclude that PQ7 brains exist from the previous calculation.
Sorry, Laksha. So you from the picture that I drew you, it is
Mhm.
clear I have constructed in type 2B an object with the same monodromy that let's
Right.
say that any given PQ7 brain. Do you agree with that? Like this guy.
Yes.
Yeah. And now the guy is smooth. That's fine.
Mhm.
But if I, for instance, let it collapse to a point, that's gonna be like, if I make these stars here, I make it very, very small, then it's indistinguishable from ordinary 7 brain. So the fact that you predict that these objects have to be there doesn't change by refining the covariation group. The fact that some of them look singular does change. But the fact that they are there, which is the physical statement, doesn't. So for instance, maybe you can find a better description of the R7 brain, which is somehow smoothed out. But that wouldn't change anything I'm telling you here.
It's a little peculiar. I mean, you've constructed BPS 7 brains as bound states of non-BPS 7 brains.
Yes, absolutely. Yes, if you're complaining I was a bit too fast there, I kind of agree actually. So the point, the only thing I can tell you is it has the same 7 brain chart as a 7 brain. There might be obstructions that I am unaware of, and there might be, more than one flavor of particular 7 brains. In fact, we know this is the case. Think of frozen singularities. Actually, one thing that we would like to do is to see if we can understand frozen singularities, like O7 plus versus O7 minus, from this perspective. Is it the O7 plus something like this decorated, like the configuration for the O7 minus decorated with Ramon fields? We don't know. But you're right, it's not obvious. The only thing that is obvious is that the charges are the same. Yes?
That's good. But as I said, it is a kind of peculiar situation, which maybe was bothering Laksha.
Yes, Miguel clarified. Thank you.
Yeah, thanks, Laksha. Okay, so we have this buddy, this guy. And so let me tell you, so we, first of all, it passed some non-trivial check with the anomaly polynomial. And then it actually, if you assume it exists, it does something very, very funny. If you have a D3 brain, because the R7 brain implements a monodromy of -1 to the FL, and C4 changes sign as you go around this. The D3, if you push it around the R7, comes back as an anti-D3. And so what that means, so the R7 is like an Alice string for D3 brains. And what this also means is that D3 and D3 can end on the R7 brain. And it essentially means that there must be Ward volume fields on the R7 that can induce in the R7 the charge of a D3 brain. And the only possibility really that you can write down for such a coupling is to assume that there's a massless freeform field on the R7 brain. In D7 brains, for instance, there's a similar coupling that couples C4 to something like F squared, okay? Where F is the U1 Ward volume, is the field strength of the U1 gauge field of the brain. But something like that wouldn't work here because you really want that this coupling remains invariant under a transformation that flips C4. So whatever you do here, if you put something like F squared, it cannot flip F4. And you also want it to be non-vanishing on S4, and that essentially singles out this coupling, okay? So this is an example. If the R7 brain exists, it seems that it should have our volume theory, something like a massless freeform. And this is, to my knowledge at least, maybe you guys know better, but to my knowledge is the first example of a word volume of a brain which has a massless freeform in its word volume. You have, of course, massless freeforms in M theory, but not in the word volume of a brain, which I thought was an interesting, quite interesting feature of this brain. Anyway, since I'm getting close to the hour, let me then maybe we can come back to this during questions. Let me just tell you the rest of the covariation groups. And you guys might be thinking, oh God, this guy still has to go through another big table. Well, actually, I don't. because everything else in SpillGen plus 2C is either related to orientifold planes. So this conjecture also recovers orientifolds. And everything else is either a class we already have, or is an orientifold, so a compactification involving orientifolds, or R7s on particular cycles or compactifications of them. So there's really nothing new at the fundamental level. There is one exception. When you have these symmetries, you can actually take a further quotient of a spin 7 manifold to give you something non-supersymmetric, which we call the half spin 7 manifold. It's a very interesting manifold because it is not spin, it's not even spin C, but it has a spin GL plus 2C structure. And we didn't really think that much about it other than noticing the fact that it exists. But other than that, really the new highlights from the spin GL plus calculation are this reflection 7 brane and this half bot manifold. And so we are left to the question that I left also in the previous in the spin MP discussion, which is omega 10. Omega 10 for spin GL plus 2C is 4 copies of Z2. What this is telling us is that from the point of view of these duality Bordism groups that we computed, there's actually up to 4 discrete theta angles valued in Z2 that you can write down. You can add as topological couplings to the action of type 2 supergravity. We could write down explicit expressions in terms of cohomology or invariance, but it's much more efficient to just tell you which manifolds they detect. So there's 4 discrete theta angles. They are non-zero in 4 particular manifolds. This is just a spin 7 manifold times a torus, HP2 times a torus, and there's a duality bundle on the torus. That's very important. There's a Milnor hypersurface, which is just some complete intersection in 10 dimensions. This is actually the most boring of them all. It's detected just by cohomology. And then there's some interesting vibration times the circle, okay, where the RP7 itself also has a duality bundle. Now, the question, there's an important physics question, which is, since I can add these couplings in the effective field theory, are they actual couplings in type 2B quantum gravity, or what happens to them? And we didn't settle the question, but and indeed in our calculation, which only uses the SL2C duality, they all look like 4 independent angles. But we observed that if we use T duality, we can relate them to M theory backgrounds, and M theory theta angles are much better understood thanks to this paper by Fried and Hopkins. So if you take this HP2 cross T2 and you T dualize, or this other guy and you T dualize on the circle to get a type 2A background, the corresponding classes you get seem to be trivial in M theory Bordism. So that seems to suggest that there's no theta angle. These 2 theta angles, they were just an artifact of us doing a 2-course approximation. As we were discussing, once you improve the covariance groups, sometimes they can go down. And it seems this is very strong suggestion that once you include T duality, these 2 guys are going to go down. This one kind of looks like it, but we're not sure. And this other one relates to the M theory theta angle discussed by Fried and Hopkins, whose existence, whether it's there or not, is still an open question. Finally, omega 11, it can be used to detect anomalies in the duality group of type 2B, and this is actually a story that we studied before with Arun, Marcus, and Jonathan in this previous paper, and led us to a prediction of a new topological coupling in type 2B string theory, but that's another story, just mentioned it for completeness. So we get to the end of our journey. I hope to have shown you at least in one particular example how you can learn a lot from the mere absence of global symmetries, and how a convenient tool to exploit this principle is covariatism, which we use to recover large portions of type 2B spectrum and to find some new things. And of course, there's many supersymmetric to extend this, like study further the Warholian theory of the R7 brane, these supersymmetric guys with exotic supersymmetry that we seem to have found. Another big direction is to include Raman fluxes in all this story. But we cannot do it alone. So I hope you will gather your party and you too will also venture forth into the lands of IIBordia. Thanks very much.
Yeah, thank you very much, Miguel. Let's thank him. So are there questions? Yes, please unmute yourself.
Yeah. Hi, a really interesting talk.
Thank you.
I was wondering if there's any point to doing this, or if you can do this, and whether there's any point to doing this with, say, T-duality groups, or U-duality groups. Is that included in this story somehow, or would that possibly give you new things, and what might it tell you?
It would be very, very interesting. No, we haven't done it. In this last slide, I kind of made an argument here that so it was just standard application of T-duality, but it's really arguing that these guys are coordinate to some other M theory guys. The framework that we have could be adapted to that. So let's say that you have your favorite supergravity. It has some big duality group. It's like a more complicated version of the SL2Z that type 2B has in 10 dimensions. So in principle, you could run the spectral sequence, compute the covariance groups, and do the same thing. And some of the defects that you would predict like that, I'm sure they would be, related to T-dualities, like some non-geometric backgrounds. The calculation of the covariance groups itself is already more complicated. It's a lot more complicated. But this is certainly another interesting direction for this. Absolutely, absolutely.
Thanks. And actually, maybe a quick follow-up. So you gave some arguments for how to study, some of the couplings that might be on this R7 brane, for instance.
Yes.
And on your conclusion slide, you said we should study the world volume theories of these guys generally. Do you have other ideas for tools of how you might do that?
Well, yeah, I kind of like, so another thing that we know about, we know bits and pieces of, we believe we know bits and pieces of the world volume theory of the R7 brane. So there is this inflow argument that tells you have something like a 3 form. Also the anomaly inflow with your anomaly polynomial suggests there's something like at least anomaly equivalent to 1 Dirac fermion of R charge 1/2. So you could throw in those two. I guess what I would like to do somehow is maybe via dualities, this can be geometrized or something in M theory, and then you can actually try to find some geometric origin for all these fields. That's what would make me happy and would make me believe that we kind of got all of them. Because with these kind of arguments, we're never going to be sure that we got the whole thing. I'm thinking something like, like the, for instance, like the 2,0 you can get by it's the world volume theory of NS5 brane, but you can also get like type 2B on a singularity, right? And so the fields you can get from some sort of like supergravity reduction on that singular background. That would be the dream. I think that would be the best way to try and understand the R7 brane, but I don't know if we can do that.
Okay, thank you.
All right, can I ask a question?
Yes.
Hi, Miguel.
Hello.
So I have a question or an issue with your argument with the 3 brane for the world volume theory.
This one?
Yeah, because you can apply the same argument for a D4 singularity. And we know the world volume theory there has nothing to do with a 3-form field.
Sorry. A D4 singularity doesn't involve any action of -1 to the FL.
It does. It involves -1. Well, it involves the monodromy matrix of -1, -1.
It involves -1 to the FL times omega. That's what it involves.
That's right. So it takes.
But the C4 remains.
Oh, I see. You're saying this 3 brane is invariant. Right.
Yeah.
Okay. So you're right.
Yeah. We really with this one maybe there's some loophole that we missed. We don't have like a proof.
Oh, okay. So I had a separate question, but I mean, another possibility here would be that if you had a non-abelian gauge theory, right, like an SU2. Right, because you could couple C4 to trace FOJF.
Very good, but here's the thing. For those guys, right, you would need to define how -1 to the FL or omega acts on them, right? And they either gonna flip because it has to be a real representation. So it's either gonna flip F or not flip F. And in both cases, trace of f squared is invariant.
Okay.
Thanks.
So if I compute Buddhism groups with SO structure group rather than spin, and I
Yes.
find more Buddhism classes,
Yes.
then will I conclude that I have more PQ7 brains than the ones that are known?
So well, right. So doing that is a bit. I mean, you shouldn't do that because let's see. I don't know. Actually, I haven't thought about that because the way we always thought about these guys. Well, oh, sorry, no. You're saying change spin to SO, right?
Yeah.
Yeah. Then it's. I don't know exactly with the duality bundles what happens, but I can tell you with the duality bundles is one of those cases. There's actually less classes in SO than in spin. As I told you, there's competing effects. There's a lot more Bordisms, but the structure also rigidifies things, so it can go both ways. You have different classes. For instance, if you just have SO, you can put the theory in CP2, for instance, which I cannot put type to be. Well, I can with a 7 brain, but yeah.
So the general logic is that I compute any kind of Buddhism group I want.
Yeah.
And then if it's non-trivial, I predict brains from the.
Well,
non-trivial.
so the Buddhism group that you compute is dictated by the symmetries of your theory. So, for instance, if you have a theory with fermions, you shouldn't be computing omega SO. Yeah, and then then within the point is that there's some backgrounds in omega SO in which your theory would be inconsistent. That's the point, right? So here, none of the backgrounds that I find here are inconsistent here. That's why this one is a refinement of the other. So it's
but
not.
If I can probably go to omega pin plus.
Well, no, this is type 2b. So in type 2b, if you do omega pin plus, like for space-time, you cannot actually, because there's no reflections. Reflections are not a symmetry of type 2b.
But in M theory, you would consider pin plus rather than spin for this reason.
In M theory, they actually have been computed. There's the best approximation that we have now to the axis symmetry type, and I think it's the best in supergravity, was computed in this paper I was mentioning by Freedom Hopkins from 2019. It's called, well, they call it, sorry, I think actually Witten called it omega MC. So basically, it's the Bordism theory of pin plus manifolds, such that they also have an twisted W1 twisted lift, interior lift of W4, which has to do with the condition for anomaly cancellation of the M2 brain. It's just that the G4 flux modulo 2 is the force differential with Nicholas, and you impose that as the data of your Bordism theory, and that's very complicated, but they computed it. I think that's the.
I see. Yeah. Thank you.
Yeah. Thanks, actually.
So if there are no other questions, let's stop the recording.